For many of the limits that we've calculated so far, it seems like at some point we just plug in the number where we're trying to find the limit, even though the limit doesn't actually care about the value of the function at the point, only nearby. So on the other hand, it would be a great shortcut if we knew when exactly it was okay to just plug in the number where we're taking the limit, because in general, just evaluating the function is a lot easier than calculating a limit. So what we're going to look at is trying to answer the question, when is it exactly that you can just plug in an x value to calculate our limit rather than using some sort of limit trick or other more complicated thing? So first, let's get a handle on what exactly we're asking. So we're going to have a limit that we want to calculate. Say the limit as x goes to a of f of x. And we're asking, when can you evaluate this limit just by plugging in the x value a? Well, if you do plug in the x value a, that would give you f of a. And what we want to know is, when are these the same? So when are these two things equal? So to understand when this is the case, let's sort of describe what each side of this equation is saying. So on the left-hand side, this is the limit as x goes to a of f of x. This is what the function f does near the x value a, and f of x is what the function f does at the x value a. So what we want to know is, what does it look like when these two things are the same? So let's try to get a handle on that just by drawing a function. So we'll draw some functions to see when this equation, limit as x goes to a of f of x is equal to f of a, we'll draw some functions where this is true and some functions where this is false, and then we'll try to get a handle on what is different about those functions. So for one example, let's just try this. Okay. So, and let me mark what value this is. Let's say maybe that's 2. So on this graph, let's find f of a first, because that's the easy part. If you look at this graph at the x value a, right here, there's a point on the graph right there, and the height of that point is 2. So f of a is 2. Now let's find the limit as x goes to a of f of x. And this is what happens near the x value a. So we can start at some x values near a, say these two. These give us points on the graph, these blue points. And then as the blue x values move closer and closer to a, these blue points, it looks like they just move closer and closer to the red point. And that means that this limit as x goes to a is 2. And since these are the same, this function, at least at the x value a, this function passes our test. It satisfies that equation. The limit is equal to the value of the function. All right, let's draw another example. Here's an x value a. All right. Let me mark this y value. So for this function, let's evaluate f of a. Just looking at the graph, the x value a is here, so the corresponding point on the graph is this upper one, because that's where the solid circle is, and so the value of the function looks like it's 3. All right, and now let's look at the limit as x approaches a of f of x. And again, we'll start with x values near a, These give us points on the graph, the blue points. And then as our blue x values go towards a, the blue points on the graph, what height do they go to? Well, on the left it looks like it's going to the y value 2, and on the right it looks like it's going to the y value 3. And that means that this limit does not exist. So this function does not pass our test. What happens at the x value a is not equal to what happens near the x value a. So this function does not pass our test. The first function did. All right, let's look at one more example. So let's have an x value a and a couple y values, maybe 2 and 3. And this time our function is going to look like this. All right, so again, we'll look at the value of the function at a. I'm just looking at the graph, that's 3. And then we'll look at the value of the limit as x goes to a of f of x. So again, choose some blue x values near a. Those give you points on the blue points on the graph. As the blue x values slide towards a, the points on the graph, it looks like they are sliding towards the height 2. So this time the limit does exist, but still the limit isn't equal to the value of the function. So this function does not pass our test. What happens near the x value is not the same as what happens at the x value. Well, if you look at these 3 examples that we've drawn, what really separates the 2 that didn't work from the one that does work is that the 2 that didn't work, at the x value a, if you were trying to draw this graph, at the x value a, you would have to lift up your pencil to jump up to some other point, right? On the middle one here, you could draw this graph by starting at the left and tracing up and to the right, but once you got to the x value a, you'd have to lift up your pencil to get up to the y value 3, and then you could continue drawing their graph. On this bottom one, you could slide up like this, but then you'd have to lift up your pencil to draw this isolated point and then jump back down. On the top function, the one that did work, you could draw this entire graph just by drawing one smooth curve without ever lifting up your pencil. So what makes the 2 functions that didn't work different from the function that did work is this jump. It's this break. And the word that mathematicians have settled on to describe this phenomenon is continuity. So a function is continuous at an x value a when it passes this test that we wrote down, when the limit as x goes to a of f of x is equal to f of a. So if your function, if what happens near a is the same as what happens at a, we say that the function is continuous at a. And the key idea with continuity is that continuity just means no breaks in the graph. All right, so continuity is our name for when it's okay to just plug in the number when you're evaluating a limit. And now we understand when that is okay. It's when there's no breaks in the graph. If your graph doesn't have a break at an x value, then you could evaluate a limit at that x value just by plugging it in. So to make sure that we understand what continuity looks like, let's look at the graph of a function and decide where it's continuous. So here's a graph of a function. And the question that I'm asking about this function is, where is it continuous? And what this phrase really means, where is it continuous, what this means is for what x values is it continuous? Well, we know what continuity looks like. Continuity looks like a graph with no breaks in it. So all we need to do is figure out where does this graph have breaks in it. So starting all the way to the left on this graph, since you could trace this graph without lifting up your pencil all the way through these x values that I'm drawing now, the function is continuous for all of these x values, all the way up until -1. At -1, you have to lift up your pencil to draw the graph, and so that means that the function f is not continuous at x equals -1. Okay, well now let's keep going past -1. Once we're past -1, we can start drawing the graph without lifting up our pencil again. We get this nice even line with no breaks in it until we get to x equals 0. At x equals 0, the graph jumps from this y value, which, why don't we give this y value a name? Maybe that's 2. So the graph jumps from y equals 2 all the way up to, well, sort of to infinity, I guess you would say. It looks like there's a vertical asymptote here. So this graph is not continuous at x equals 0. All right, once we get past x equals 0, we can start drawing the graph without lifting our pencil again. So this function f is continuous for all of these x values until x equals 2. Once we hit x equals 2, again, there's a break in the graph, and that means that the function is not continuous there. So f is not continuous at x equals 2. And then beyond x equals 2, it looks like there are no more breaks in the graph. And so f is continuous at all of the x values greater than 2. So this graph is not continuous at x equals -1, x equals 0, and x equals 2. And that means that f is continuous for all x values different than -1, 0, and 2. Another way to say this is that f is continuous on the intervals. Well, let's see, it starts being continuous for large negative values all the way up to -1, but it's not continuous at -1, so we have to chop out the x value -1. And then from -1 up to 0, it's continuous, but it's not continuous at 0. And then from 0 to 2, it's continuous. And then it's not continuous at 2. And then from 2 up to infinity, it's continuous. So if you wanted to answer this question using interval notation, this is how you could write the intervals where f is continuous. All right, one last thing to see about continuity is that if a function isn't continuous, so these points where f is not continuous, these are called discontinuities. And they actually come in 3 different types. So the discontinuity at -1, if you look at sort of why there's a break in the graph here, it's because the graph jumps from one value to another. And so this kind of discontinuity we call a jump discontinuity. I'll abbreviate discontinuity by discont. All right, so that's a jump discontinuity when the graph just jumps from one height to another. At x equals 0, there's a discontinuity. Well, it's sort of because it jumps, but what it actually is jumping to is infinity. And so if one of the limits at your x value is infinity, we call that discontinuity an infinite discontinuity. All right, and then at x equals 2, well, the function actually isn't jumping here. It's just that there's a hole in the graph. And when there's just a hole in the graph, you could fix this discontinuity by filling in the hole, by modifying the function just at this single x value. And since you could remove this discontinuity, we call this a removable discontinuity. Removable discontinuity. The reason that jump discontinuities and infinite discontinuities aren't removable is because if you tried to fix, say, this discontinuity at -1 just by changing a single x value, what x value would you change? I mean, at x equals -1, if you tried to move the function down to this lower height, there's still a discontinuity there. If you try to put the value for the function at x equals -1 in the middle somewhere, like this, there's still a jump discontinuity there. To get rid of the discontinuity at -1, you would have to take the graph and change it not just at -1, but also nearby. You'd have to bend it all the way upwards like this, and that's pretty drastic surgery. But a removable discontinuity you could fix just by changing the value of the function at a single x value. X equals 2 in this case. All right, so we started with the question, when is it okay to evaluate a limit just by plugging in the x value? And we called that phenomenon continuity. And we decided, or we realized, that it's okay to evaluate a limit just by plugging in an x value when there are no breaks in the graph at that x value. If your function isn't continuous, the discontinuity comes in one of three flavors, either a jump discontinuity, an infinite discontinuity, or a removable discontinuity.